x with a minus y, right? So put everything in terms of y, then you can carry out this integral. And that's what we're going to do. This becomes rho times y squared. So keep the y squared inside, but the x replaced with a minus h. So this becomes a minus h, a minus y times h times y squared dy. Now, if you integrate everything based on y, what will be the limit? The lower bound, of course, 0. What's the upper bound?
A.
Yes, very good. Upper bound is a, right? For the value on y-axis from 0 to a. And then, of course, h is constant, take it out. And this becomes rho times h times this integral, which, of course, you know how to do. I will just make it obvious for you. This is going to be x times a times y squared minus y cubed dy. Of course, you know how to do this, right? So I'm going to give you the answer, and the final answer is 1/12 of rho times h times a quadruple. Now, because we know this is total mass, so you can also write Ixx in terms of total mass, and that's going to be 1/6 of total mass times a squared. This is our mass moment of inertia with respect to the x-axis. Now, if you look at this, what about Iyy? What about the mass moment of inertia with respect to not x but to y? Think about that if you want to rotate this three-dimensional wedge with respect to the x-axis. You probably notice that on the xy plane, it's actually symmetric, right? In fact, you can actually swap x-axis with the y-axis, and the result wouldn't be any different, correct? But not z, not z. X, y are actually symmetrical to each other. And that means on x-axis, how do we know? On x-axis, it has the same dimension, a. On y-axis is also a. And the height on the x-axis is h. The height on the y-axis is also h. That means x, y are the same. That makes sense? If they are the same, what does that mean? That means their mass moment of inertia are the same. So for this Iyy, you do not have to do any calculation because we know, because of symmetry, Iyy equals Ixx equals 1/6 of total mass times a squared. And we found the second one because of symmetry. You may want to put it here due to symmetry. Okay, now next, IZZ. This will be step 3, right? Now, how do we calculate the mass moment of inertia of this with respect to the z-axis? You notice that when you calculate rotation with respect to the z-axis, you're looking at this. You're not looking at taking the strip. The strip must be cut like this. You have to cut this kind of strip. And when we do that, we notice this. We notice this. The unit volume, z of course is the out of, well, actually the inward direction, that's the z-axis, like that. Now, what is the center of gravity of this triangle? the center of gravity is, if it's triangle, is 1/3, right? From 0 on x-axis, and also the 1/3 of the length. Or so 1/3 of A and 1/3 of A. So the center of gravity is right here. This is G. Of course, it should be symmetric. Now, if you look at the book, in the back of the textbook, this is table. And we are looking for the mass moment of inertia of a triangular plate. Of course, in the back, you do not find this triangular plate on here, because it's the rotation with respect to the perpendicular direction. But if you notice that, if you look at this rectangular plate, the case, Ix is 1/12 of the perpendicular dimension, and Iy is 1/12 of the perpendicular dimension. For Iz is 1/12 of the mass times the perpendicular dimension squared and sum of the squares. So what does that mean? That means that the Iz direction, the mass moment of inertia in the z direction, actually has something to do with the dimensions on x and also on y. So here, this is what we have. So that the unit volume can be defined by Izz, which equals to rho times r squared, and r here has something to do with x and y times dv. And you integrate on both sides, you're going to get this all together. So this expression actually equals to this. It's equals to rho times r quadruple over 4a squared times 1/3 of a squared plus pi times r squared over a times 1/4 of a quadruple. And this whole thing times dy. So this is the unit mass moment of inertia on the z-axis. So don't forget about this whole thing has a dy. This. So to get the value of Izz, what we're going to do is just to integrate this whole thing on the z-axis. And of course, we're going to integrate it from 0 to h, and this value Iz will eventually become this. It's rho times pi times a times, actually plugging z, this actually becomes total mass times r squared over 6 plus a squared over 2. So what is r? R is the distance from the center to this. R is from 0 to the center of gravity. In this case, what is R? R is a over 3 times what? Times square root of 2. Because R is the diagonal distance from the z-axis to the center of gravity. So this is R here. And then this will be our values for Izz. Now, next value. By definition, paradox of inertia equals to paradox of inertia is defined by if you're calculating IXY, and this is on my notes, page 60. Yes, it's on 60. The unit product of inertia with respect to the XY axis equals to the unit products of inertia with respect to the principal axis at the center of gravity. So this one here is at the center of gravity, at G. And note, if you already notice that for this problem, if you look at this wedge from the top, you will notice that we actually didn't choose the center of gravity for this problem, right? If you look at this is X and this is Y, we want to find out what is the mass moment of inertia.